This is Dr. Cynthia First at the University of Utah, and today I'm going to be talking about the basics of circuit representations. We'll talk about the definitions of voltage, current, and resistance, the idea of ground, which is also called reference or neutral, variable resistors and resistive circuit sensors and how they might be used in our circuits, and how we measure all of this. We'll spend some time on series and parallel elements and the ideas of node, path, and loop. Voltage is the source that drives our circuit. A DC, or direct current voltage, is something that doesn't change with time, such as this battery. It's constant. When we define voltage, we always show where the positive and the negative part of the voltage is, and if I had turned the battery upside down like this, I would have had positive here and negative there. The current is shown with an arrow, such as this DC current right here. We use these other two symbols to represent DC voltage also. The long line here is always positive, and the short line is negative. If we just draw a circle, we still have to define the positive and the negative parts of the voltage. The ground, or reference or neutral, is where the voltage is equal to 0 in our circuit. When you build a house or other building, you take these large ground rods and you drive them into the ground or the dirt, and you connect your circuit onto it like so that ground literally is the 0 point for your voltage. But if you have something like your cell phone that's not really connected to ground at all, we still need to define a point in the circuit that we call the reference or the 0 point. So someplace in this circuit we're going to say that that is the 0 or ground point for that circuit. AC, or alternating current voltage, is something that varies with time. So as a function of time, our voltage goes positive and negative sinusoidally like so. We still define a positive part of our circuit and the ground or neutral point, like shown here. And if we have something that's AC, we just put this little squiggle or sinusoidal sign above it. A resistor is used throughout our circuit. It changes voltage into current, or it changes the amount of current that you have. This is a picture of a resistor. That's literally what you'll buy and solder together. And this is the circuit representation. Ohms is the unit that we use for resistance. Variable resistors are resistors that you can change. You can completely control the resistance of this resistor by putting your screwdriver right there and just turning it. You can turn this one with your fingers. The idea is that you have a basic resistor shown right here in red and a sweeper arm like so. The resistance between A and W here is controlled by where the sweeper is in our circuit. If it were right here, you'd have very little resistance, but if you were over here, you'd have quite a bit. We show a variable resistor as a resistor with an arrow through it. Now, when you buy a resistor, just the small resistors that I showed you that had the lines like this, there are only so many certain standard resistor values that you can get. There are a lot of them, but there are only so many, finite number. But a variable resistor can take on any resistance between its minimum and maximum value. A potentiometer is the 3-terminal variable resistor, such as I showed you in the previous slide, and a rheostat is a 2-terminal variable resistor, essentially the same thing, just packaged differently. In order to use resistors as sensors, we want to have something that changes its resistance depending on the environment. A thermistor changes its resistance if the temperature rises or falls. A piezo resistor changes its resistance if the pressure changes, and an LDR changes its resistance if the light intensity changes. You'll be using these in the lab. In order to measure voltage, we use a voltmeter. It's also called a digital voltmeter or a DVM, and the picture shown here is representative of a typical voltmeter. There are 3 places to connect your cables. Connect your red cable or positive cable onto the V, and your negative cable or black cable onto the COM. Common is another name for ground. So if you wanted to measure this battery, right here like so, you would connect your red cable where you wanted to measure the positive part of the voltage, and your black cable where you wanted to measure the negative part, and your reading would be that this D-cell battery is a 1.5 volt battery. We also show our voltmeter in the circuit as a circle with a line through it. Generally the line is at an angle, and if it's AC, it will have a little squiggle like this. In order to measure resistance, you hook up the voltmeter the same way, and you put it across the resistor. So right here, we could measure the value of this resistance. Unlike voltage, measuring resistance does not matter which way you put your leads. So you could measure this resistance this way, or you could swap it around and measure it that way, and you'd get exactly the same value. We show a ohm meter or a resistance meter in the circuit as a circle with an ohm in it. Measuring current is done differently than measuring either voltage or resistance. The black lead is still in the common slot, but the red lead is in the A or ammeter slot. We measure the current coming in like this from positive to negative. So we actually hook our ammeter up so that the current comes in and runs through the ammeter. We show a DC ammeter as a circle with a line through it, and we show the AC ammeter as a circle with a squiggle. Let's suppose that we wanted to make a circuit, a touch lamp for example, where we would touch the base of the lamp and the light would turn on. The engineer would draw the circuit this way. That's the circuit diagram, and that's mostly what we'll be talking about in class. You would then build it by laying out a PC board, and it would have holes here that you could solder your elements on, and that would be your actual circuit. Here are several common elements that you show in your circuit. The most common, of course, is a wire, and if the two wires cross each other, like this, we can assume that they are connected. If they have a dot in the middle, we know they're connected for sure. In order to show that they are not connected, we'll actually show one wire jumping over the other wire. That's two conductors that are not joined electrically. Here's our resistor and of course our variable resistor. Capacitors and inductors we will work with later in the class. Here's our battery, our DC battery, and here is our 12-volt AC source. We haven't talked yet about current sources. They're shown this way. A switch is typically shown closing like so. We'll be using op-amps in Chapter 4. We won't really be using transistors in this class. The voltmeter and ammeter are shown here, and we'll later be talking about dependent sources and light-emitting diodes as well. Next, let's talk about the basics of circuit topology. A branch is a single element, such as a resistor or a source. Here is an example of a branch. Right there, here's an example of another branch. A node is a connection point between two or more branches. So they're shown here. Very often we will show nodes as little dots on our circuit, but really the node is the whole connection from one element to another. So there's the whole node. An ordinary node is something that just connects two wires like this. An extraordinary node connects more than two, such as this one right there. A loop is a closed path where you start at one point in your circuit and you just move around back to the same point. In order to define several points in our circuit, let's find the ordinary nodes and extraordinary nodes in the circuit. All the ordinary nodes are in yellow. The extraordinary nodes, here's one that's red, here's one that's green, here's an orange one, and the ground one is black. So an ordinary node contains just two wires, and an extraordinary node contains more than two. I'm going to show you how to get in the habit of color-coding your circuit in order to be able to use that to define things that are in series and parallel. So take a close look here how the nodes move from one element. The color fills in all the way to the next element. If I were doing an extraordinary node, I start with my color here, and I fill in all the way to my next elements. Now in the next video, I'm going to show you how to use that to define things that are in series and parallel.